So thanks everybody for letting me come and talk. And my name is James Myers, and I'm with Intel's NonVolatile Memory Solutions Group, so NVM Solutions Group. That's the team inside of Intel that make the SSD products, and the team that's bringing exciting new technologies to market like Intel Optane Memory, that I'm sure a few of you had mentioned might want to learn a little bit about it. So it is St. Patrick's Day. It's your lucky day. So pay attention closely. You're going to see something in the presentation that we've not shared publicly until today. So you guys get to see a little peek of something that nobody else has seen. Hopefully you want to share it. But we're not really here to talk as much about Optane, although there'll be a little bit. I want to talk about data integrity. What's the value of your data? And it's one of those hidden secrets. So what we're going to do is go through a little bit of flow, and feel free to jump in, hit me, be really challenging on me, because it's my first time at one of these events. So I'm hoping to have to dance. It's Dancing a Jig Day. We're going to talk a little bit about... Perfect. Thanks, Howard. We're going to talk a little bit about storage in the industry and what we see SSDs doing to change things, how end users are appreciating them, so a little bit of marketing fluff, and then I'll go through that quickly. Then we'll talk a little bit about interfaces and how they're changing and what's coming, Optane. And then we'll dive in specifically into data integrity, and that'll be the majority of the talk, and where my partner Vinod is going to come up and actually hopefully dazzle you with some physics. We're going to talk about ones and zeros and all sorts of fun things like that. So feel free to jump in. So level setting, hopefully this is not education for any of you. I just wanted to make sure that we're common on terms. Scale up storage, which traditional storage systems versus scale out, meaning it's a shared network and generally using either replication or erasure coding, some other sort of availability rather than RAID and complete redundancy of all the hardware. So scale out on the right and scale up on the left. Easy enough. And the reason I say that is because at Intel, especially within the both the storage and the SSD group, we see huge traction in the industry of things moving away from traditional scale up in some cases and moving to scale out. So we see growth in both areas. But why do we see the growth in scale out? Well, scale out growth, we think, is driven a lot by faster storage, by SSD technology. It really is the advent. I mean, there's nothing that new about scale-out storage. Left-hand networks had it a long time ago, but it really hasn't taken off until recently, and I think that's because of the faster storage media. We see
the faster network.
And the faster network, absolutely, absolutely, and the faster network. So we see some end users using it in a couple of different ways, and there's a lot of value. And it's exciting to see the industry getting aligned around the value of scale-out and faster storage. And so a couple of examples. These are examples that may be new to some of you, but Flickr from Yahoo, and you're going to hear a little bit about this in the second presentation. But Flickr from Yahoo was able to use a scale-out storage, a Ceph model, and they were able to double the number of users per server by adding an SSD, adding some Intel software to their cluster, and David's going to talk a lot about that in the next presentation, so I won't spend too much time on it, and increase their throughput. And so obviously, huge value for them. They can get the same job done in half the number of nodes. So they're pretty excited about that. What we also see, and that's hybrid, by the way, that's hard drives and SSDs. We also see big enterprises embracing scale-out storage and all flash. And so the example on the right, the largest grocery retailer, and if you take a look at the notes and flip through the back in the backup that you'll see, there's a link to a blog and you can see the name of that grocery retailer. They have actually deployed an all-flash vSAN into their enterprise environment. So they're taking and moving away from traditional scale-up storage and moving to scale-out hyper-converged all-flash, where they're using NVMe and SATA SSDs. And the reason is because of the faster deployments. It's really all about OpEx. They'll spend a little bit on CapEx, and they'll save a ton on OpEx because they don't have to worry about rebalancing the performance across all of their SAN frames. They can spin up instances tremendously faster. Instead of taking weeks to even months sometimes, it was a matter of hours to be able to go and give someone a service, and it's trending toward days. So they're able to give a cloud-like service to their infrastructure, and so they're really excited about it. And even the analysts, the big analysts out there are saying all-flash storage makes a lot of sense. Gartner just came out with a study a month and a half ago, and they said the ROI from moving your enterprise storage from traditional spinning media to an all-flash of some type, something like the all-flash vSAN, pays for itself in less than 5.4 months because of the OpEx savings. It's all about the OpEx savings. So we see the market going that way. Obviously, we're excited about that. We also see other shifts in the market, and that's one about interface. And so a lot of people say, well, SAS interface has been around a long time, and it's great. Why would we want to use something other than SAS? It's got all of these great features. It's well entrenched. This is the basic answer. So what we've been trying to make sure that people understand is the performance that each of these storage interfaces can present to the application layer. So what we're showing here is a snapshot of a VMware ESXi environment. So we've built the ESXi environment, and then we put operating systems within each of the VMs. Then we're running IO meter within those VMs on top of a file system. So all of the stack that you would have in a normal application usage is here, with the exception of the application. And this is the IO performance that you can get from each of these three interfaces in that environment. So we run a mixed 70-30 workload, and we throw that at a SATA drive, a SAS drive, and an NVMe drive. And you can kind of see the differences. In the top, you've got latencies, read and write latencies for 4 workers, and on SATA, on SAS, and on NVMe. So you can see the read latency is lower for the SATA drive and even further lower for the NVMe drive as opposed to SAS. And the write latencies are about the same SATA and SAS, and then the NVMe brings down the write latency as well. So we're reducing that latency in the stack, storage optimized interface. So we really see, and it ultimately gives you almost 2 times the performance of SAS to go to NVMe at the application layer. So the real application can appreciate double the storage performance by going to NVMe from SAS. That's the reason we see it going that way. So we see all the scale-out storage moving from SATA and SAS, moving to NVMe, and we see that happening in a big way this year, especially as new systems and platforms come out with the U.2 form factor and as many as 24 or 48 U.2s packed into a 2U box. So there's about 15 platforms out there that are doing that today.
James, what's the asterisk against NVMe for?
That's the asterisk that we put in to make sure that people understand that we don't own the name. Okay. It's a trademark and branding sort of thing. I don't know where the disclaimer went. It should say other trademarks are property of others. Good question.
It's the big company legal department.
Hallelujah. Hallelujah. Come on, I must be putting you guys to sleep. So now, where's it going in the future? It's going in the future from NVMe. And why NVMe? Because of 3D XPoint and Optane. So hopefully you all have heard about 3D XPoint memory. And if you haven't, I'll just briefly go over it. A new non-volatile memory technology that is going to replace NAND and potentially in some cases replace DRAM. We see this coming in. And why? Because it's 1,000 times faster. It's non-volatile. It's 10 times denser than DRAM. It's 1,000 times faster than NAND and 1,000 times more endurant than NAND. So that really opens up a lot of possibilities with this sort of a change. You get cost structures that are, because of the density, much closer to NAND than they are DRAM. And you get performance that's much closer to DRAM than it is to NAND. And it's non-volatile. So you can totally change the game if you're to move this into the memory semantics. You can totally change how applications are written and utilize this non-volatile memory. Things like NVDIMMs exist for reasons that there are benefits in this space.
So those numbers are like unbelievably fantastic. Are they day one numbers? Are they 5 years down the line numbers? What should we read into them?
Potential, or is this out of the box?
Good question.
Okay. All right then.
This is data that we've shown. Actually, this is not new. This is data that we showed at Oracle Open World, and this is the performance. So, answer your question. It's the performance that you can get out of the memory cell itself. This is the performance that you get when you take that memory cell and you put it into an SSD on a PCIe form factor at a bare metal level. Okay. So there's no file system. It's just FIO in an Oracle Linux environment. And we're seeing things go from 80 microseconds of latency down to 9 microseconds of latency on a PCIe interface. So the PCIe latency itself is in the neighborhood of 7 to 8 microseconds. Right? So that means it's about 1 microsecond of media latency on top. Right? And this is something that we actually showed it running. This is a single queue depth workload, so we're talking about very low queue depth. And this happens to be a read-only, the data that I'm showing, but read-write. The interesting thing about the 3D XPoint is that the read and write latencies are the same. It's not like NAND, where the read latency is different.
This isn't just out of the box.
What is Optane?
Optane is an Intel brand that we're putting to represent the combination of 3D XPoint memory with the Optane system ingredients that we wrap around it in order to make a system-level product that's going to meet the needs of the market.
Got it.
So when you hear Optane, that's going to be means means very, very fast non-volatile memory.
So what kind of NVMe SSD only gets 11,000 IOPS?
This is actually our P3700 with a queue depth.
I guess the important thing is, what are the
Queue
IOPS?
depth of 1. It's a queue depth of 1. It's 4K random reads, queue depth 1. So this is actually very common and very good. The interesting thing about all the IOPS numbers that people like to quote, data sheets are always at queue depths of 128. When you get into real usages and applications, usually the queue depths are 4, maybe 8, maybe. If it starts to go up above that, people start to reprovision and rebalance things because they don't want to deal with the latency that starts to come up. So people will quote huge IOP numbers, but in reality, it's in the 100, 150,000 IOPS in the useful range. This is the lowest end where people are most interested in latency, transactional latency, high frequency trading. Where latency is everything, they'll dial the queue depths down as low as they possibly can. Just to make
So
sure.
you really could have made this much more impressive by just using a ridiculously large queue depth.
The interesting thing about the Optane technology is that it is within an SSD. It is going to fill the bandwidth at a very low queue depth. Somewhere around 8 will max out the bandwidth. Right? We'll be filling it right up. So I wouldn't have used it. I could have made this number a lot bigger. The latencies would have gone way up. The latency gap could have gotten a lot bigger. It could have been better at a queue depth of 4 or 8. But yes, this is just an example at the low end. And that's where we'll go on the next slide. So this is what's new. What does that mean in terms of application performance? So I showed you that VMware example where I put all the stack and I ran IOmeter inside a Windows operating system with a file system and ran those VMs. Read and write latency, you see they're the same. So you see they're the same, and actually the latency in this case was in the 35 to 40 microseconds. So, gee, that's a lot. Well, there's a lot of software in the way. A lot of software. There's an operating system and there's an ESXi hypervisor. And what does it do? This is again a very similar workload to what we did for the NVMe SATA SAS NVMe, so 7030 workload. So it goes from 66,000 IOPS with that workload at the application layer with the NVMe drive to 160,000. So 2.5 times faster application performance when you take Optane memory inside an SSD. That's what you're going to see. And that's delivered to the application. And then when you put it on a memory bus and you take out that 8 microseconds of latency from PCIe, it's going to change the game even way more than that.
I think that shows that the hypervisor and virtualization to a certain degree is a big problem now.
It's a challenge. It's an opportunity. I wouldn't call it a problem. 2.5x performance, you're just dropping it in. That's not a problem. That's fantastic.
As a vendor, it's an opportunity. As operations guys, it's a problem.
Yeah.
Fair enough, fair enough. We are working very, very closely with VMware to help them optimize this, and they've shown us some things. We expect this to get even better before we release the Optane product in an SSD.
Speaking of releasing the Optane product, when is that happening?
As you know, we're Intel. We don't ever pre-announce products. Good question, though. I wish I could tell you.
I tried, guys.
We have publicly stated that it's expected to have a product this year.
Got it.
Right? And obviously, you're seeing more and more demos. We're showing public information here, so that gives you some indication. So we're really excited about the technology, but that's not really what we're here to talk about today. So I did want to talk about, though, ultimately the fact that PCIe, scale-out storage, it's happening in a big way. All the analysts are agreeing. It's what's fueling the growth in the storage industry. It's kind of transforming IT. It's very interesting and exciting to be in the IT world again because of this transformation. It's the biggest transformation in storage in decades. And everybody agrees it's moving that way. It's moving that way because of SSD technology. SSDs are moving to NVMe interface, and soon we'll have Optane, which will make it even better. So expect this to continue. So what do we really want to talk about today? We wanted to talk about data integrity. So my little phrase here. Never trust spinning rust.
Really?
Really.
You had to go there.
Never trust spinning rust.
It's not moving.
That's right. True, it's not moving.
And disk drives don't have rust anymore, so that's,
Never trust spinning rust. So hard disk drives, there's lots of studies out there about failure rates. There's a couple of studies out there about data integrity. And people don't really like to talk about it. storage is expected to, you write data, you expect to read it and get it back. And hard drives, unfortunately, don't always do that. And a whole bunch of hard drives were surveyed in an organization, and they found that 0.46% of the hard drives, the nearline hard drives, or 0.04%, were changing a 1 to a 0 or 0 to a 1 and not telling you about it. They're giving it back. It's wrong. They don't tell you it's an error. RAID's not going to catch this. Only secondary data integrity systems around this are going to catch it. So it's really kind of scary, right? And why is it scary? Because it's expensive. It actually happens, believe it or not, and it's even published. So all of this is data that I was able to get through the web, where you look at even big corporations are challenged and brought to their knees. One of the examples here is on a blog from Netflix, where they were their DVD transfers, their distribution centers were shut down for 3 days. That cost them a tremendous amount of money, and they traced it back to a data integrity problem where a 1 flipped to a 0 in some application code that took down all of their operations servers. So 3 days of business lost because of a 1 turning to a 0 and nobody telling anyone about it. Amazon lost 36 hours of S3 service because of a data integrity problem. A 1 turned to a 0 in their environment, and they traced it down to that. So they actually have proof that that's what happened. And it shut them down for 3 days. And Facebook was down for 48 hours where nobody could get to their photos or their friends' photos. Oh, I know.
The teenage.
That one wasn't quite so expensive.
That was a good one.
But it was expensive for Facebook.
Yeah, ad revenue.
It was expensive for Facebook. So Gartner did a big study
and the
again.
poor parents who had to put up with the teenagers.
Had to talk to them.
No, the ennui.
So Gartner did a cost estimate. They looked at a whole bunch of different information and studies, and they said on average it's $5.6K or $5,600 of every minute of downtime. That's the cost. And so you can see the cost for 3 days or 36 hours or 48 hours are huge. And it affects all of us in other ways as well. I mean, there was a Wired magazine article about the Toyota stuck accelerator problem, where they said they've eliminated almost all the possibilities, and the most likely possibility was it was a data corruption problem inside the controller in those modules. Now, they don't have proof. These guys have proof. Toyota doesn't have proof, and they would never say it. It was Wired magazine that said it. But it's just interesting. It affects us, and it's expensive. So it's kind of scary when you think about transitioning to new storage models. Traditional scale-up storage guy. You like to watch? I didn't even know you're a watch guy.
Oh, he's a watch guy.
I know that now. I learned that last night. But you need to know what's inside the system to really understand what's going on.
Spinning rust.
Yeah. You need to know what's going on in the system. And so the interesting thing is the storage companies, the big guys that do scale up, have known about this for a long time. And they've been putting all kinds of systems in so that users don't ever have to worry about it.
I would say most is an exaggeration.
Really?
Yeah. I don't think most storage systems go so far as doing background scrubbing. And so, yeah, the problem is bigger than we believe.
So bit rot is a real problem.
Oh, yeah.
That's a real problem. Yeah.
Oh, yeah.
I'd say that probably applies even more so to the software-defined guys.
Well,
It's unknown.
what do you think?
The bit rot, well, I don't know. I'm not a flash expert. I'm just saying the bit rot part on magnetic media has been known since we came out with magnetic media. So the question is, will flash help? It's you know what I'm saying? It's a new thing. So
I do.
will in 10 years or 15 years, we'll find out a different problem that we didn't know existed.
Yeah, but there was a NetApp paper 2 or 3 years ago that something like 25% of production file systems have undetected corruption.
Correct. It's absolutely right. It's a real problem.
Yeah.
It's a real problem. And, to the point that some of the systems put protections around it. They'll put end-to-end protections around it. They'll use features like T10 diff, or some applications, very few, will use features like DICs, where they put extra CRCs, and they know. Some file systems like XFS have some capabilities to identify some of these, but in most all cases, they go undetected. And they go undetected, and if it takes down your system, it gets detected. If it's 3 days of downtime, you know about it. But if it's your data, who knows? Who knows? It's interesting. So we look at this when we look at SSDs, and the reason we think about it when we look at SSDs, you're going to see some data from Vinod, and we're going to talk about it, because go back to the 0.042% of every enterprise hard drive has turned a 1 to a 0 and not told you about it. Even the worst SSD that we tested was about 2 times better than that. Even the worst SSD that we tested. So that's good news, but still, they're there at way too high a frequency. When you put a few thousand SSDs in your environment, you're going to have a lot of challenges.
Because there's also, the problem also happens during the transport. So
it can.
Yeah.
It can, but most of those systems have extra CRCs and retry policies, and that takes it down to 1 times 10 to the minus 28, 30 in most of those systems, and we're talking about 0.042 for a hard drive.
That's not the same number. That's not the same number. Wait, let's not get.
Per bit
that's
spread.
not the same. I'm just saying that the chance that it will happen and the number of hard drives percentage is not the same. That's like over
That's true.
time. That's like the number.
That is for a year. Yeah, you're right.
Yeah.
Versus a rate.
Yeah.
That's fair.
Yeah. I'm not saying it doesn't. And I agree with Howard, though. I think I think we're in total agreement here.
Okay.
This is a problem.
It's a bigger problem.
I wanna see
It's a
what- I
bigger
wanna see
problem
what-
than you're claiming it to be, so we'll let it go.
If it's a bigger problem than I'm claiming to be, why aren't people talking about it?
Because outside of this room, 90% of the people who use storage systems don't know.
They don't know.
Right. Think back to, deduplication hash collision concerns. People were concerned about a problem that's got a likelihood of 1 in 10 to the negative 60th. And here we got a problem that's 1 in 10 to the negative 20th that they're ignoring because it's an old problem they're used to.
Howard, repeat what you said about the NetApp study.
There was a NetApp study
Yep.
published at FAST
Okay.
2 or 3 years ago.
There's a key word I'm waiting for.
That 20% of the file systems have undetected
There you go.
corruption.
That's why it's not talked about more.
Because it's undetected.
There you go.
Yeah.
It's undetected. Does it matter?
So how does it know?
No,
it's 20?
undetected is worse. I'm going to go out on a limb and say that 100% of unknowns are not known about.
Way to put yourself out there, Stephen.
But, if there's an undetected error at Los Alamos National Bank that puts $1 million in my bank account, that's not a problem for me, but it's a problem for Los Alamos.
Right. Most
Only
of
if
those
you
don't
try to
find-
take the money out. I want to see what's next. We can talk like this
Fair
for
enough.
2 hours.
So what causes a silent data corruption in an SSD? Obviously, in hard drive storage, data
Leprechauns.
corruption can be caused by lots of things. One of the most common is actually mechanical movement of off track within their ability to recognize it.
Yeah, but at today's scale TLC, the difference between a 3 and a 4 is what, 40 electrons? And 10 of them escape, and then you don't know.
Not when you move to 3D NAND. Not when you move to 3D NAND. But so what
Well,
causes
not when we move to 3D NAND until 4 more generations when you shrink it back to that size.
the surprising thing, and Vinod can talk to it, but the surprising thing is it's not the media. The media is actually very, very insensitive to flipping a 1 to a 0, and there are great encoding schemes that we put on it, the same way they do in hard drives as well, encoding schemes. But it's other things. It's actually this sort of stuff.
Cosmic rays.
Cosmic rays. They really do exist. So I'm going to pass it to Vinod, and he's going to talk you through what actually is the physics behind it and what you can do about it.